Friends, welcome to the fourth lecture in module 3. In this lecture, we are going to talk about short term fatigue damage, this is a lecture in module 3 where our focus is towards risk assessment and reliability applications. We all believe that fatigue reliability is one of the direct application of finding probability of failure of a given system under cyclic loads, where we have been discussing it continuously for about few lectures from now. So, we are talking about the short term fatigue damage in this lecture, which is online course on risk and reliability of offshore structures. Now, the power spectral density function of the wave elevation for low and moderate sea states cannot be actually strictly assumed to be a narrow band. Moderate and low sea states cannot be strictly assumed to be a narrow band. You would realize from the last lecture that it is essentially important that the cyclic load effects caused by the ith spectral wave need to remain as a relevant process. That is why we model this from a Rayleigh distribution. Strictly speaking, in reality the low and moderate sea states cannot be actually modeled as a narrow band process, whereas for extreme sea states this can work. Okay. Now, therefore, the stress response due to a broadband sea state will continue to remain as broadband. Particularly when the dynamic response is not dominated by large amplification factors in any given natural modes of vibration. Therefore, the wave induced stresses in offshore structural members to be very specific, in the absence of large dynamic amplifications which are exposed under, let us say, under moderate sea state, will continue to remain as broadbanded, which cannot be ignored in fatigue calculations. So, one cannot simply say I am going to idealize it as a narrow band process, the stress ranges, and try to get the assessment, which may not be correct, because in reality the moderate and low sea states are generally not narrow banded, they are broad banded. So, therefore, they have significant humps near the wave spectral peaks the presence of significant humps near the wave spectral peaks are really the concerned one, or maybe in the vicinity of the fundamental frequency will become more severe. Is now important, because all through you understand that we are talking about the stress wave amplitude relationship for either your 2 segment SN curve or 1 segment SN curve. Okay. That is how we are assessing the fatigue damage so far in the all discussions what we had discussed in the earlier lectures. So, here the peaks present near the wave spectral peaks, and if that peaks happen to be closer to the vicinity of the fundamental frequency, then the assessment of fatigue what you have been doing earlier without any modified methodology may give you a wrong assessment of fatigue damages. Therefore, what do you do in such case? For such cases, the closed form expression for stress cycles and the fatigue damage derived from the spectral analysis will not be very accurate. The closed form expression to compute fatigue damage will not be correct, okay, as said by Wishing and Light in 1980. Therefore, a general approach to a broadband correction is to assume a suitable counting algorithm. So, one need to actually account for a broadband correction on the estimated values of fatigue damage, or alternatively one can go for a suitable counting algorithm. To estimate the stress cycles in the time history of the stresses generated by the time history of the stresses generated by the time domain analysis. So, then one can use this estimate of stress change history to obtain the damage. Then one can compute the damage based on the stress history obtained as above, okay, from this process. Instead of assuming the stress history as a narrowband process, you go for a typical counting algorithm. Counting means for a given stress cycle time history, you try to find out how many number of times or what is the cycle by which the stress has exceeded a specific threshold value. So, rain flow counting method is seen as one of the effective alternative method which is very popular in offshore fatigue assessments. So, the narrow band and wide band are connected by the following relationship if you really wanted to adapt a correction factor to the fatigue estimates what you done from the narrowband, you can connect this by a factor lambda. If you know the estimate of fatigue damages from a narrowband theory what you already assume, you can always adapt the correction factor alpha as we said here to account for the wideband corrections. In this case, dWb denotes the wideband process obtained from the time domain analysis, and dNb denotes the narrowband process obtaining by making a narrowband assumption, whereas alpha lambda is what we call as a correction factor. The damage from the wideband can also be directly obtained from the rain flow counting method, whereas the damage from the narrowband has already have closed form expression which has been given and discussed at length in the last set of lectures. Now, the issue is to establish a suitable value for the correction factor lambda. Now, the discussion is to establish a suitable value for lambda. Now, there are very few spectral shapes which have been considered based on which the lambda can be computed. So, the variation of this correction factor depends on the spectral width parameter let us say epsilon, and the second could be the exponents used in SN curve approach. Now, these are studied by various researchers in detail by let us say Ortiz and Chain. Similarly, Lutes and Larson. Let us say given a stress spectrum which is essentially a wideband, the sample stress history can be generated using computer simulation. That should not be a big problem, because once I know the spectrum defined, can always find the stress history. Rain flow method can then be used to count the stress cycles in the simulated record. The stress cycles let us say of exceedance or positive upcrossing barriers in the simulated record. So, one can follow this approach. Therefore, a narrow band and wide band can be connected by the relationship shown from equation 1. Now, the Wishing rainflow factor lambda is expressed by the following equation, which depends on the slope or the exponents of the SN curve and the spectral width parameter, which is a very important discussion or decision between the narrow band and the wide band, which is given by A plus 1 minus A 1 minus epsilon to the power B, where equation number 2, where A is given by 0.926 minus 0.033 m and B is given as 1.587 m minus 2.3. Equation 2. So, we all know that m in this case refers to the exponent of the Sn curve, and epsilon refers to the spectral width parameter. Of course, m refers to the Sn curve corresponding to low cycle ranges only. That is important. Okay. So, one can either find out directly the upcrossings of the stress cycle history from the wide band of the real C state using the rain flow, and using Wishing's factor one can estimate and convert the data, the damage obtained from the narrow band to that of the equivalent wide band. Why we are interested in wide band? Because of a simple reason, as we stated earlier, the C states of medium and low cannot be actually processed or analyzed as a narrow band process. Okay. However, in the whole context there are many uncertainties in fatigue analysis. Let us talk about the uncertainties in fatigue analysis. May be arising from the wave loads, essentially linearization of the wave loads, that can be one major problem. Inaccurate stress concentration factors, what we call SCF. Inappropriate fatigue design curves, there can be many uncertainties. Now, the fatigue damage estimates are sensitive to these errors due to various factors or influence caused by these factors in the overall estimate. Therefore, to check whether the system is safe under the fatigue damage estimate, one can use the relationship D should be less than or equal to 1 by FDF where FDF is called fatigue design factor. Usually greater than 1. It is implied that the total damage D, which is cumulative over the design lifetime T of the structure, is what we are estimating it. Alternatively, if the calculated long term fatigue damage, let us say T0, so in equation D3 we are trying to compare the total cumulative damage caused to the system, that is the fatigue damage. If the life of the structure is T, then and the long term fatigue damage estimate is D0, which corresponds to a year. Then the fatigue life can be calculated, because one is interested in knowing the safety check. Fatigue life can be calculated. The fatigue life can be given by Tf is equal to 1 by D0, equation number 4. Once we know this, then either the member or the joint is to be considered safe against fatigue failure if the following condition is satisfied. So, the condition to be satisfied for safety against fatigue damage or fatigue failure, because that is what we are interested in, reliability or application of reliability, is that Tf should exceed or equals Tx into Fdf. Now, various international codes give appropriate fatigue design factors as guidelines. Okay. Interestingly, while evaluating the damage integrals, in estimating the fatigue life, let us say the fatigue damage integral contains basically n number of cycles to failure. Okay. The variance of the exponential distribution probably may be a different density function. So, there can be variations in the distribution function used for the stress cycles or stress ranges. Let us consider an integral damage integral, let us say d, where d is given by integral of this, which is going to be integral of, let us say, dn by n, where dn is m into f of s ds Now, the variable m in the equation 7 denotes the number of waves in a long term or a short term climate. And f of s would be the probability distribution function of the variable s. Of course, this depends upon the approach used to model S, okay, that is important. So, if let us say f of s is given by let us say 1 by delta minus s by delta to the power y minus 1 exponential minus s by delta to the power nu, let us say equation 8, then this could follow a variable distribution function. So, it all depends upon what is the particular PDF you are using for estimating the dn value, based on which your integral is evaluated. So, the damage expression integrals will consist the following form. Let us say integral I can be integral from 0 to stress value of q, which can be 1 by delta s by delta raised to the power nu minus 1 exponential s by delta nu minus by a s minus m, where m is the exponent of the Sn function, plus integral of s q to infinity. We are splitting this integral into two parts, which is going to be 1 by delta s by delta nu minus 1 exponential minus s by delta nu divided by a s minus m ds. Okay. Equation number 9. While evaluating this integral, let t be expressed as s by delta to the power nu. Then one can use gamma functions. Then the integral in equation 9 can be replaced as, let us say the gamma functions can be gamma function of p and z is z to infinity t to the power of p minus 1 e to the power of minus 1 dt, which can be also said as gamma of p minus gamma 0 p z, provided p is greater than 0. Equation 10. Gamma 0 p z is also written as 0 to z t p minus 1 e to the power of minus t dt, and z is actually s q by s to the power mu. These gamma functions can be easily evaluated using a MATLAB program. Okay. So, there are various uncertainties in fatigue estimates. We know that the input values for fatigue damage estimates, which are important as slope of the Sn curve to be used for the design, the spectral width, the material characteristics, variation in input load effects, etc. may cause errors due to many reasons. Therefore, the basic fatigue data which is used in developing the SN curve is actually the source of large scatter for these variations. So, fatigue damage models, especially under random stresses, can be only approximate, it cannot be accurate. There can be defects and discontinuities at welded joints which can complicate this process of estimate further, because the crack initiation and propagation depends upon the discontinuities at the point of origin of this fracture. There is also an important aspect that relates to the fatigue damage models. The statistical models which are generally used in ocean climate modeling can also have inherent errors. The force or the load model being used for estimating the wave and current forces are only approximate, and they can also often used from empirical relationships. The hot spot stresses used in fatigue damage estimates contain also uncertainties, because a variety of stress analysis procedures, each having different accuracy, are adopted in practice. Therefore, all these factors relates to accumulation of errors in structural modeling for obtaining the nominal stresses, which is one of the important input for estimating the fatigue damage. Therefore, the evaluation of hotspot stresses using stress concentration factors etc. can also lead to lot of uncertainties in fatigue damage estimates. Further, in offshore structures, influence of corrosion will also matter. Dynamic amplification of large displacement structures like complaint structures can also be a problem. The cathodic protection, which is being used as an inherent part in the design, can also have influence on fatigue strength estimates, which are actually not modeled appropriately using the literature. Therefore, it is very interesting for us to actually apply these uncertainties to some extent in an experimental model. So, a tubular joint is investigated using experimental and analytical procedures. The results are compared, which I will discuss in the next lecture. So, friends, we are now going to discuss a very interesting problem where the tubular joint are actually loaded on experimental setup, and the stress concentration factors are derived based upon the loads estimated using the sensors on the failure joints. Then they are compared with the load carrying capacity, which are estimated based upon the empirical relationships advised by international codes, to actually understand the reasons for these uncertainties. So, as discussed just now, there are many uncertainties which lead to a general statement making that fatigue estimates in offshore structures cannot be accurate. They can be relatively better if you start using the experimental models for fatigue damage estimates as well, which we will discuss in the next lecture. Thank you very much.